This video is about how logarithms are inverses of exponential functions. This is AP Precalculus topic 2.10. If you appreciate this content, please give it a like. Just as we can graph previous functions, we can also graph logarithmic functions. Here's the general form of a logarithmic function. Notice that b must be greater than 0, b cannot equal 1, and a cannot equal 0. Because exponential functions and logarithmic functions are inverses of each other, we would expect the characteristics of the input-output values of an exponential function to become the characteristics of the output-input values of a logarithmic function. Recall for exponential functions over equal width input value intervals, the output values change multiplicatively. For example, notice that f of x for equal length input value intervals, successive output values are 2 times bigger than the previous output value. That's how you know f of x is an exponential function. For logarithmic functions, these two properties of the input and output values are reversed. This time, notice that the output values are equally spaced, while the input values are changing multiplicatively. Each input value is 2 times as big as the previous input value. This is how you will know that you are dealing with a logarithmic function. Example 1. Selected values for several functions are shown below. For each, determine if the given function could be logarithmic, exponential, or neither. For part A, I notice that the input values are equally spaced, so we are going for either exponential or neither. To see if there is a common ratio, divide each term by the previous term. 8 divided by 16 is 1/2, so that's the first ratio. 4 divided by 8, again, that's 1/2. 2 divided by 4 is 1/2. So we do have this multiplicative variation in the output values. Each output value is 1/2 the previous output value. H of x is exponential. For k of x, we notice that the output values are equally spaced, so there's a chance that this will be logarithmic. Now we look for a common ratio between the input values by dividing each input value by the previous input value. So we see that the first ratio is 3. And then again, 90 divided by 30 is also 3. 270 divided by 90, again 3. When the input values change proportionally for equally spaced output values, the function is logarithmic. For part C, we have neither equally spaced output values nor equally spaced input values. So we can judge neither logarithmic nor exponential. So just put neither. For part D, we notice that the output values are equally spaced. So we are going for logarithmic. Let's see if we have a common ratio among the input values. Dividing each input value by the previous input value, we get a common ratio of 2. So L of x is logarithmic. If we were asked to explain or justify our answer, we would say something like logarithmic because the input values are proportional for equally spaced output values. Or we could say the input values change multiplicatively. Exponential and logarithmic functions are inverses. So if f of x is equal to b to the x power, and g of x is equal to log base b of x, then f and g are inverse functions. Therefore, f of g of x will equal g of f of x, which will equal just x. Also, recall these two important properties of inverse functions. The graphs of inverse functions are reflections of each other over the diagonal line y equals x, and if the point x1, y1 is on the graph of f, then the point y1, x1 must be on the graph of f inverse. Example 2. Let f of x equal 3 to the x power, and g of x equal log base 3 of x. Show that f and g are inverse functions by showing that f of g of x equals g of f of x, which equals x. Let's start with f as the outer function. So f is 3 to the x power, so I'm going to rewrite this as 3 to the parentheses power. So I have 3 to the parentheses. And then inside goes the inner function, which is g of x. But then g of x is log base 3 of x. Log base 3 of x is the exponent that turns 3 into x. So here we have a 3. And this is the exponent that turns 3 into x. So the answer is going to be x. Alright, in practice when we look at this we think the base 3 and the log base 3 cancel each other out and you get x. Now we flip it around and we start with g as the outer function. So g is log base 3 of x, so let's rewrite this as log base 3 of parentheses. And inside the parentheses goes the inner function, which is f of x. But f of x is 3 to the x power, so now we have this. When you evaluate a logarithm, you ask yourself, what power will turn the base into the other number? So we are asking ourselves, 3 to what power is 3 to the x power? Well, obviously 3 to the x power is 3 to the x power. I know it feels silly. In practice, we just say to ourselves that the log base 3 and the base 3 cancel each other out, and you get x. Example 3, a portion of the graph of the exponential function k of x equals 2 to the x power is shown on the graph below. Sketch a picture of k inverse, which equals log base 2 of x on the same coordinate grid. Let's identify a few key points from the original graph of k of x. For example, we see the points 0, 1 and 1, 2 and 2, 4. The corresponding points on the graph of k inverse will be 1, 0, 2, 1, and 4, 2. So let's see, 1, 0, 2, 1, and 4, 2. Also, notice that the graph of k of x has a horizontal asymptote, the x-axis. So the graph of k inverse will have a vertical asymptote, which is the y-axis. So k inverse, which equals log base 2 of x, will look something like this. Example 4. The exponential function h of x equals a to the x power contains the points 2, 3 and 6, 27. Find the average rate of change of y equals log base a of x over the interval from 3 to 27. Recall that the average rate of change of f of x on the closed interval from a to b is given by f of b minus f of a divided by b minus a. So the average rate of change of y will be y at 27 minus y at 3 divided by 27 minus 3. Since h of x includes the points 2, 3 and 6, 27, then h inverse will include the points 3, 2 and 27, 6. But h inverse is the log function log base a of x. So when we need to find y at 27, we can just look right here. H inverse at 27 is 6. Similarly, y at 3 is just h inverse at 3, which is 2. So we just have to simplify this. 6 minus 2 is 4, and 27 minus 3 is 24. 4 goes into 24 6 times, so the answer is 1 over 6. Example 5. The function f is given by f of x equals log base 2 of log base 3 of x. Which of the following is an expression for f inverse of x? To find f inverse, the first step is to switch x and y. So I'm going to have x equals log base 2 of log base 3 of y. So here I have switched the y and the x. So somehow I need to solve this equation for y. If I want to make the log base 2 go away, I can do that by dropping a base 2 on both sides of the equation. Base 2 and log base 2 cancel each other out. If this was log base 3, I would put a base 3. If this was natural log, I would put a base e. Anyway, the 2 and the log base 2 will cancel each other out. So on the next step, we will have 2 to the x power is equal to log base 3 of y. So I'm closer to having y by itself, but now I want to get rid of the log base 3. Guess what I'm going to do to make the log base 3 go away? I am going to drop a base 3 on both sides of this equation as well. So the base 3 and the log base 3 will cancel each other out, leaving y by itself. So y is equal to 3 to the 2 to the x power. This is going to give me f inverse, but I just need to rewrite it. Actually, do I need to rewrite it? So this already matches one of the answer choices. I see this matches answer choice B right here. 3 to the 2 to the x power. That's exactly what we have right here. Example 6. The table above gives values of function f for selected values of x. Which of the following is a verbal representation of f inverse, the inverse of function f? We can make a table of values for f inverse by reversing the input and output values from f of x. When we see that the output values are increasing by the same amount, there's a chance that f inverse might be logarithmic. Let's see if the input values are changing multiplicatively. Let's see if there's a common ratio between the input values. Let's divide each input by the previous input. So 4 divided by 2 is 2. So we have a ratio of 2. 8 divided by 4, that's 2 again. 16 divided by 8 is once again 2. So when the output values are equally spaced and the input values are being multiplied, in other words, when the input values show a common ratio, that's a sign that you are looking at a logarithmic function. Specifically, the answer is B. F inverse is logarithmic with output values increasing by 1 every time input values double. Example 7. The exponential function g is given by g of x equals 5 to the x power. Which of the following expressions defines g inverse of x? You get the inverse by switching x and y and then solving for y. So if I switch x and y, I get x is equal to 5 to the y power. Once I solve for y, that will be the inverse. So we can rewrite this in logarithmic form. That's how we solve for y. So we see that the base here is 5. So that means I'm going to have log base 5 like this when I rewrite this in log form. The other two numbers, the other two variables, are going to switch sides. So the y is going to come over here by itself, and the x is going to end up over on the right hand side as log base 5 of x. So this is the inverse, and the answer is A. Example 8. The graph of the exponential function f is given. Which of the following could be a table of values for the inverse function of f? I'm going to use these 2 points to write an equation for f of x. So we have the point 0, 1 and the point 1, 2. The model of an exponential function f of x is a times b to the x power. Let's use these 2 points to find the values of a and b. To begin with, if we plug in 0 for x, then we are going to get 1 for f of x. So that means I have a times b to the 0 power is equal to 1. But b to the 0 power is automatically going to be 1. So that leaves me with a is equal to 1. So now I just need to find b. So I can use the other point now to find b. But so far I have f of x equals, and I know that a is 1, so this is 1 times b to the x power. I think we can agree that I don't really need to put the 1 here. So I'm just going to write f of x equals b to the x power. If I plug in 1 for x, I should get 2 for f of x. So that means b to the 1 power is going to equal 2. Well, b to the 1 power is just b. So we really just found that b is equal to 2. So that means f of x is 1 times 2 to the x power. In other words, f of x is 2 to the x power. Now let's find f inverse by switching x and y. So this will be x is equal to 2 to the y power. Rewriting this in log form, I get log base 2. The x and y switch places, so I have y is equal to log base 2 of x. Let me show you why I know that D is going to be the answer, and that will automatically show why A, B, and C could not be the answer. So f inverse is log base 2 of x. That means if D is the answer, then f inverse at 32 better give me 5 for the final answer. So if I plug in 32 for x, then I have log base 2 of 32. When you evaluate a log expression, you ask yourself 2 to the what power is equal to 32. And we know that 2 to the 5th power is 32. So that's why the answer is 5. So f inverse at 32 is 5, just like it says. Let's try the input of 4 and see if we get an output of 2. So f inverse at 4 would be log base 2 of 4. So you think to yourself, 2 to the what power is equal to 4? Obviously 2 to the 2nd power is 4. So that's why the answer here would be 2. And that's exactly what we see. Let's look at one of the other answer choices for comparison. For example, option A has the input-output pair 5 and 32. That means if I do f inverse at 5, I should get 32 for the answer. However, f inverse at 5 would be log base 2 of 5. And then you're supposed to ask yourself 2 to the what power is equal to 5? Well, there's no power that turns 2 into a 5. So you know that A is not the answer. Option B. If I plug in 5, I should get 25 for the answer. but f inverse at 5 would be log base 2 of 5. Well, we just talked about this. There is no power that turns 2 into a 5. So B cannot be the answer. And finally, option C has the input of 25 with an output of 5. But if I plug in 25, then I have log base 2 of 25. And when you ask yourself 2 to what power is equal to 25, there is no power that turns 2 into 25. And certainly 2 to the 5th power is not 25. So C is not the answer. Example 9. The function f is given by f of x equals log base 3 of x. Which of the following could be the graph of f inverse? The parent function for logarithmic functions looks like this. Since there are no reflections or translations, log base 3 of x is going to have this general look to it. Specifically, we have a 1 point here, which is always going to be at 1, 0. We have another point. If we plug in 3 for x, like let's say this is 3, something over here, then we have log base 3 of 3. 3 to the 1 power is 3. So we do have the point 3, 1 that is on this log graph. I'll stretch it out a little bit more. The inverse of a log function is an exponential function like this. It's the reflection over the line y equals x, and since the point 1, 0 is on f of x, then the point 0, 1 will be on the inverse. Since the point 3, 1 was on f of x, the point 1, 3 will be on the inverse. Let's scroll through the options so you can take a look, scanning for the options that look exponential. So I think you can see that we have narrowed it down to either B or C. A is clearly not an exponential graph, neither is D. So between B and C, we can use the fact that the point 1, 3 is on the correct graph. So the point 1, 3 is not on this graph. However, the point 1, 3, there it is, right on the curve. So the answer is C. You can always use the base to come up with a convenient point that's on the curve of a log graph. So just for example, I'm just making something else up. If I had h of x is equal to log base 5 of x, then I would immediately know that the point 5, 1 is on the graph. Right? Because if I plug in 5, then I would get log base 5 of 5. And of course that's going to equal 1 because 5 to the 1 power is equal to 5. So you can always use the base to get a point. All right? In fact, I guess just in general, if I have h of x, is equal to log base b of x, you're guaranteed that the point b, 1 is on the graph. Example 10. The function f is an increasing function such that every time the output values of the function f increase by 1, the corresponding input values multiply by 4. Which of the following could define f of x? Well, the answer is obviously going to be D because of everything we've been talking about in this video. We have learned that when the output values are equally spaced, while the input values have a common ratio, that's when you know you have a logarithmic function. So the answer is D. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.